Well, welcome everybody. It's good to see you all. This is the British Interplanetary Society, the West Midlands branch. I'm Bob Stanton. I'll be hosting today. And today we've got a talk from Emily Creedy. I'll be introducing her in a moment. But just before we do that, I've got a few quick things I just want to run through. Oh yes, if you would like to actually help out with running our branch, please let us know or stay at the end and we can have a chat. We could certainly use the help. BIS membership. So I haven't checked the stats today, but normally about half of you are not members and you're missing out because we've got all of these videos that you could just live off of for months. You've got Spaceflight magazine, the leading astronautics magazine, the Journal of the British Interplanetary Society, Space Chronicle. We get all sorts of things you should actually, on projects you can be involved in. I can't recommend it enough. If you're not a member already, think about joining today. I'll stick the link in the chat once Emily starts talking, although pay attention to Emily first. HQ are asking, so if anybody's got any material suitable for publication in JBIS, Space Chronicle or Spaceflight, please contact HQ or the editors. They'd be very pleased to hear from you. And then that brings us on to today's speaker, Emily Creedy. So Emily is already a graduate. She's an engineering graduate and she's doing Masters by Research over the next 2 years. And I think it's really good to see the next generation coming up, looking at these new ways of doing things, the idea about having hybrids that can have multiple points of ignition, really exciting stuff for long missions. And she's been telling me that they're actually planning to patent some of the things that they've been coming up with. So she might be a bit candid, a bit cagey today when she's talking, but we'll see what happens when we get to the questions and answers. Daniel Jubb, I know you're there. Emily is available for internships. She's got, she should be looking for some, I think some experience in industry as well, while she's actually doing her 2-year masters. And I think with that, that's all I'm going to say. It's introduction. So, Emily, over to you.
Thank you. I'll share my screen. As Bob mentioned, my name is Emily Creedy, and I will be talking to you today about an introduction to hybrid rocket motors and laser ignition techniques. My supervisors are Lishan Gullah, Philip Charlesworth and Adam Jones at the University of South Wales. I graduated last July with a bachelor's degree in aircraft maintenance engineering and currently at the bottom of the little arrow in Wales. So today I will mainly be looking into the history and development alongside technological maturity, as potentially we are looking into a pattern. I can't shed too much technically, which brings me into defining what a hybrid motor is. So a hybrid motor use the propellants in 2 phases. You have the solid fuel grain right here, and then you have the oxidizer tank where it's admitted through the valve, and passes through the injector and is then ignited along the surface of the fuel grain, and that is the regression. Their development started around the same time as solid and liquid systems due to the need for safer, cheaper and more controllable alternatives to the both liquid and solid systems. Now, a lot of people probably can call them hybrid engines. That is not correct. Engines generally have moving parts where hybrid motors do not, and that is why they're motors, and the same thing applies to solids. So initially, the work started in the early 1930s in the Soviet Union by the Soviet Group for the Study of Reactive Motion. And this led to the first ever hybrid motor launch, which you can see in the picture is the GIRD-9, and it was in August 1933. So these initial launches, initial developments, led to America picking up the technology in the 1940s, particularly by a society called the Pacific Rocket Society. They frequently tested in the Mojave Desert, which is now where NASA's Jet Propulsion Laboratory tests. And their work primarily consisted of like material developments. So, for example, some of their first tests with hybrid motors used experimental Douglas fir, or XDF, for the nozzle. However, initial tests completely obliterated it, little nozzle made out of wood. But they kept going. They tested XDF4, but the stand wasn't strong enough. It just broke away and landed under a nearby car. But finally, they tested XDF23, which was actually aluminium, not wood, and it successfully flew to 30,000 feet in 1951. So in the 50s, more and more developments were taking place, but something quite interesting that popped up was the reverse hybrid motor. So this is where the oxidizer was solid and the gas or liquid phase was the propellant. These were meant to be quite cheap. That was their main driver for development. However, there were a lot of problems experienced with rough burning and poor performance, and they just generally aren't very stable, so they haven't really seen any development since. But significant progress was made during this time, particularly by two employees of GE, to realize the distinct advantages of hybrid motors at the time, which were the lower development periods, lower costs, and the simplified plumbing. And these developments in the 1960s led to 6 main sponsorships by the US Navy, which carried out significant works on the combustion behavior and internal ballistics. So this is where Schlerin photography took place, and Schlerin photography, if I'm pronouncing it right, is the photography of fluid flow. So this really helped us realize the ignition process, the combustion process, and it basically gives all the information we know today. And then we had the era of enlightenment from the 60s to the 80s, and this is where significant materials research in particular occurred for hybrid rocket motors, particularly in the US and Germany. And this saw the first proper integration of hybrid motors by the US, which was for the Target drone program. They were 3 programs, which were Sandpiper, HAST, and Firebolt, and in the bottom right, you can see a picture of one of the target drones from the HAST program. But then it kind of makes you think, if all this development happened leading up to the 80s, why haven't they seen more integration? Part of this reason was the materials at the time were very hazardous. They were quite toxic, weren't safe to handle, and generally weren't seen as mature. As in the 1970s, NASA created something called the Technology Readiness Level. This readiness level is determined by NASA as part of their decision-making process for what is used in their missions. So for both solid and liquid systems, they have been used very widely. The Saturn V, for example, you would probably know, quite famously used in the race to the moon, and then the solid motors that are used for the space shuttle boosters. Additionally, space solid motors are used for tactical weapons, as they are very easily ignited very quickly. And this really furthered both of the systems' development. And for that reason, the technology readiness level of both systems can reach up to 9, which is the highest, and again has been the default choice. And you can see by comparing each system's advantages and disadvantages, it also reflects their development levels. So if I start with the solid, you can see that the disadvantages, it's difficult to manufacture, it has a lower specific impulse, and also higher emissions. These are things that will just happen with solid motors. It's part of their design. And the same with liquid systems. They are complex. You can see in the diagram, there's a lot that goes into them. This means they're quite big, they weigh a lot, and also they're very expensive. These are properties of the system that will never change. However, with hybrid motors, the most commonly mentioned disadvantages I have found in literature is the lower efficiency, low regression rates, and a lack of repeatability. And these three factors are all easily rectified with more research. So although they did emerge around the same time as the other systems, they haven't seen the same interest. There is one program that has given more interest, that is the AMROC Aquila launcher. I think that is starting to re-emerge again. However, in the 90s it did drop off due to financial issues. But due to NASA's recommendation of a technology readiness level of at least 6 to be implemented in their missions, hybrid motors have not been used because their readiness level is 5. So the reason they kind of stagnated at around 5 is something known as the valley of death in development. So in levels 4 to 7 in the chart, this is where researchers such as myself and other university students need to go to industry. They need to ask for funding and make a good case for industry to invest in these new technologies. This is quite an expensive, quite a risky process perhaps for industry, and that has led to a lot of potentially promising technologies to not mature at the rate that they should have been. However, recent years there's been a 700% increase in hybrid motor research. This is great progress for hybrid motors, and I personally think that a likely cause is that they're very accessible. You can see these, well, even with the competitions for university students, there's a competition each year where universities build their own hybrid motors. And so they're accessible, they're easy to design, they're safe, and they're cheap.